Okay, in this video we're going to look at a couple of extra exercises from section 5.6. So first thing we're going to look at is the derivative, finding the derivative of f of x equals arc sine of x over 5. So if we write generically, if f of x is equal to the arc sine of u, where u is a differentiable function of x, then the derivative f prime is going to be u prime divided by 1 minus u squared, all under the square root. So when we're taking the derivative here for this specific problem, u is x over 5, so u prime will be 1 over 5. So taking that derivative, that is going to be 1/5 divided by the square root of 1 minus x over 5 quantity squared under the square root. We'll go ahead and make a common denominator there. 1 is the same thing as 25 over 25 minus x squared over 25, all under the square root. Okay, so then we're going to get 25 minus x squared over 25. Okay, and then that's going to be the square root of all of that. And we can use a property of square roots, and we can write that as 25 minus x squared under the square root, and then divided by the square root of 25. So that's where we're going to go with that, because then we can simplify the square root of 25 down. Okay, so let's go ahead and take a look. So we have 1/5 divided by 25 minus x squared under the square root, divided by 25 under the square root, which will be equal to 1/5 25 minus x squared, and times 1/5, because this is the same thing as 5 down here, so we can write it there as a 1/5, and then you see that you have like factors of 1/5, so those are going to end up absorbing there, and so we get 1 over 25 minus x squared is that derivative there. And in the next additional example, letter F from our note handout, we're going to be taking the derivative of 25 arc sine of x over 5. So that derivative will be 25 over 25 minus x squared. Okay, so let's go ahead and look at the next one. So letter F from our notes is F, it's not F this time, it's y equals 25 arc sine x over 5, and then minus x, and then square root of 25 minus x squared. So y prime, so as we mentioned a moment ago, the 25 arc sine of x over 5 is going to have a derivative of 25 divided by the square root of 25 minus x squared. That was exactly what we were taking the derivative of on the last example. Now when we do the derivative of x times the square root of 25 minus x squared, that's going to be a product rule. So the derivative of x is 1, so we just get 25 minus x squared under the square root, and then minus x, and then derivative of the 25 minus x squared all over the square root. The 1/2 power will come down, and then is 25 minus x squared, and then to the minus 1/2 power, and then by the chain rule, the derivative of 25 minus x squared is negative 2x. Okay, so what we're going to do is we're going to get a common denominator between everything. This is a square root of 25 minus x squared in the denominator, so this middle piece will try to get that common denominator there and see what we got going. Alright, so 25 over the square root of 25 minus x squared minus 25 minus x squared, and we'll just say over 1, and then we're going to give it the common denominator, so we're going to multiply it by the square root of 25 minus x squared over the same thing. Then rewriting, you got a negative here and a negative here, so those will offset each other. The 1/2 and the 2 will also offset each other, and then the x times the x will give us an x squared. So we're going to need x squared, and then 25 minus x squared under the square root. Alright, so that's going to be 25 minus, and then when we multiply these two together, the square roots will absorb. We got the minus right there. 25 minus x squared, and then plus x squared, all over the common denominator. And so the 25s are going to absorb, the First x squared is going to become positive, so we're going to have 2x squareds on the top there. So we have 2x squared over 25 minus x squared under the square root. And then that would be the derivative. Okay. The last example we're going to take a look at is we're going to find all the relative extrema of arc sine of x minus 2 arctan of x. We'll go ahead and mention what the domain of arc sine is. That's minus 1 to 1, including minus 1 and 1, and then the domain of the arctan is all real numbers. So the domain of this function is going to be the smaller of the two. It's going to be minus 1 to 1, the intersection there. And so when we're looking for extrema, we'll probably use the first derivative test, which means we're going to take the derivative, set it equal to 0, and find your critical numbers. Critical numbers are where the first derivative is equal to 0, so where the first derivative is equal to 0, or the first derivative does not exist. And of course, that would be for values of x in the domain. So that would give us like corners and cusps most of the time. Okay, so we got to take the derivative, and then what makes this such a fun problem is the algebra. Okay, so again, we're going to only consider this on minus 1 to 1. So f prime of x is going to be equal to 1 over 1 minus x squared. That's the derivative of the arc sine. Minus 2 over 1 plus x squared. That's the derivative of the 2 arctan. Now we're going to be looking for horizontal tangents, so we're going to set it equal to 0. And the one place where this is going to be undefined, that's going to be at 1, and that's actually it's going to be plus or minus 1. And those are going to be endpoints anyway, so we'll look around plus or minus 1 anyways within the domain here. Okay, so we're going to go ahead and clear the fraction. So common denominator is square root of 1 minus x squared times 1 plus x squared. So we're going to go ahead and multiply both sides of the equation by this. So this is where all the fun algebra comes into play. So then we have 1 plus x squared and then minus 2 square root. So 1 minus x squared equals to 0. And if you remember from college algebra and pre-cal, this is a radical equation, so we would like to isolate a radical, and then it's a square root, so we would want to square both sides, okay? So we're going to isolate that radical, so we're going to add the 2 square roots of 1 minus x squared to both sides, and then we'll go ahead and square both sides. Now, since I'm running out of real estate and I try to avoid the Dorseri logo over here, we're going to go ahead and go on to a new slide. Okay. So 1 plus x squared, and then that's going to be equal to 1 minus x squared. We'll go ahead and square both sides. That'll undo the square root. So foiling 1 plus x squared times 1 plus x squared will give us that. And then we'll have 4 times 1 minus x squared. So that's 1 plus 2x squared plus x to the 4th. Distribute the 4. 4 minus 4x squared. And then this is a 4th degree polynomial, which is going to be kind of like a quadratic. So we'll go ahead and add 4x squared to both sides and also subtract 4. We have x to the 4th plus 6x squared minus 3 is equal to 0. And sad times, this is not going to factor, so we're going to use the quadratic formula. It's not quite quadratic, but is what we call quadratic form. If you imagine that, for example, u is x squared, then u squared is equal to x squared squared, so that'd be x to the 4th. So this thing looks like u squared plus 6u minus 3 equals to 0. So we did stuff like that in college algebra and pre-calculus. And so it is in what we call quadratic form, so we can use the quadratic form. And so it's going to look a lot like the quadratic formula, except for instead of having x, we're going to have x squared equals. And so that's what we're going to do here, and see what we got going on. That's going to find us where our horizontal tangents are. Okay, so negative 6 plus or minus square root 6 squared minus 4 times 1 times negative 3, all over 2 times 1. And that's going to be negative 6 plus or minus the square root of 48 all over 2. So that tells us x squared is approximately, so I went ahead and put that in my calculator, so that's the negative version, or x squared is equal to approximately 0.464 and etc. Now I threw out the negative because if I take the square root of the negative number, I'm gonna get imaginary numbers, and we're keeping it real on this stuff here. So no imaginary numbers here. So we're not going to worry about that, and that's not in our domain anyways. -1 to 1. Okay, so we're going to take the square root, and that's going to tell us x is approximately plus and minus 0.68. And we'll go ahead and draw our number line. Okay, so -1 is the end of the domain, and then negative, or beginning of domain, however you want to think about it. And then we have two critical numbers, -0.68 and 0.68. I guess you can consider the 1 and the -1 critical numbers because the function is undefined at the derivative is undefined at those 2 points. So what we're going to look at is we're going to test in each one of these intervals, and we're going to test in the first derivative. If the first derivative is positive, that means the function is increasing. If the first derivative is negative, that means we are decreasing on that interval. So that's our Cal 1 stuff. So for example, if I happen to go from increasing to decreasing, then I'm going to have a maximum there. And then let's say I went from decreasing to increasing, I would have a min here. And then we're at the end of the line here, so this is going to be a minimum, and then we're at the end of the line here, that's going to be a maximum. So that may very well be what happens there. There might be other possibilities, but we're going to go ahead and pick a number between -1 and -0.68, between -0.68 and 0.68 and 0.68 and 1, and that's going to tell us whether the function is increasing and decreasing. Of course, we're going to plug that into the first derivative. Okay. So let's pick -0.7 would be good. And let me go ahead and write down what the derivative is. And we'll go ahead and use -0.7, plug it into the derivative. And we're not interested too much of what the number is other than is it positive or negative. Okay, so here we go. And then when we plug that into our calculator, that is going to be approximately 0.06. That is positive. So that means we are increasing from -1 to about -0.68. Okay. And then usually we don't say we're increasing at a particular endpoint, so we exclude we don't put a bracket at -1. Okay. Now we'll pick 0. That's in between -0.68 and 0.68. You can pick any value in between those two, and it'll always be the same sign in the first derivative. So f prime of 0 will be 1 over 1 minus 0 squared under the square root minus 2 over 1 plus 0 squared. It's going to be -1. So that tells us we are decreasing in between -0.68 and 0.68. Okay. And since we went from increasing to decreasing at so we went from increasing to decreasing at -0.68, that tells us we have a maximum there. All right, now we're going to try 0.7, and all we got to do is change this to a plus, change this to a plus, and change that to a plus. So we don't have to redo the computations there, and so that's going to be 0.06 also. So we're going to be increasing from 0.68 to 1, and because we went from decreasing to increasing at 0.68, we're going to have a minimum there. Okay. And so we'll put in our other part there. So we got our increasing and decreasing intervals. Now this was not specifically asked for, but because we're finding all the mins and maxes, the relative extrema, we can go ahead and grab that anyways. Okay, so we're also going to have a minimum at -1, and then we're going to have a maximum at 1. And so we'll also be interested in those values, okay? So if we want to know like the XY coordinate for the min and the max, we need to plug that into the original function. The original function is going to tell us position. Okay, so we're going to have a max at x equals negative 0.68, and so we're going to plug in negative 0.68, and we're going to plug it into the original function, and then that's going to tell us what the y value is. Okay, so that is going to be about 0.447. So our maximum is approximately negative 0.68 and 0.447. We're going to have a minimum at x equals positive 0.68. So we'll go ahead and plug in 0.68 into the original function. That's going to tell us the y value. Okay, so plugging that in. And that's going to be approximately negative 0.447. And looks like I'm being a little bit dyslexic here. I think this is a 447. Okay. And then a minimum, so right as an ordered pair. We're also going to have a minimum at -1 because we increase from -1 to negative 0.68. And we'll have a maximum at 1 because we increase from 0.68 to 1. So we'll go ahead and plug in -1 and also 1 into the original function, and that's going to tell us the y coordinates. Okay, so arcsine of -1 is negative pi over 2, minus 2 times arctan of -1 is negative pi over 4. That's going to be 0. So min is at -1 and 0, and then f of 1 is going to be arcsine of 1 minus 2 arctan of 1. Arcsine of 1 is pi over 2, minus 2 arctan of 1 is pi over 4. So that's going to also give us 0, so we have a maximum at 1 and 0. So we have located all the extrema. I went ahead and threw this into Dorseri and took a screenshot of it so we can take a look at the graph here. So here's the graph. There's a min at -1, 0. There's a max at 1, 0. We have a max at negative 0.68 and 0.447, and a minimum at 0.68 and negative 0.447. And then notice that we go increasing to there and increasing here. So those are the two places we saw the increasing, and then we had the decreasing from negative 0.68 to 0.68. Now, if we wanted to find the concavity, we'd have to look at the second derivative, and that'll get quite more messy because of the nature of the functions we have here. Okay, so that is it for these extra examples on the 5.6 notes.